All right. I had a little more to share with projectile motion from chapter 10, but it's just in the way of review, just more of the same. Let it sink home a little bit. 10. And then the latter part of the lecture will be chapter 35, as listed on WebAssign, on special relativity, the theory of special relativity. I choose that because, well, I think it's very interesting. And a lot of times in these type of courses, you don't get to some of the cooler modern physics-y stuff because you're so busy back at Newton's time, with forces, which is very important and foundational, as you can hopefully at least tell or appreciate at this point. But you're poised now to understand the basics of the special theory of relativity, understanding all of the motions and velocity and accelerations, momentum and energy. So I can share with you the assumptions Einstein based his theory on and a lot of the implications. Just, make your mind go, what? So half of you are going to like it and half of you aren't, because it is a different way of thinking. And the world isn't quite there yet, even though we rely on it. Phones would be useless if we did not account for the special theory and the general theory of relativity. If it did not take those into account, these would be inaccurate, for example. So the people that at least design that are using it. It's just we don't really have to think about it in everyday life. So I'll share that with you. But first, shooting. All right, I got a projectile launcher here. I can change the angle. Let's see what we're set to. We're set about to 60, so I'll start with that. So it's spring-loaded. I can push it down and compress the spring. See, I'm exerting a force with my hand, and I'm going to compress the spring a certain distance. Force times distance is work. So I'm going to take my chemically stored energy and transfer it into the spring as elastic potential energy. And that's how much work I do. There's one. I'm going to go a little further. There, to the middle range. So now it's stored. When I release it, the energy will come out of the spring and turn into what form? Kinetic energy. It'll have an initial velocity. And we can know exactly how fast it was going, right? If we knew how much energy I just put in there. Correct? Anybody not think they could figure that out? Raise your hand. Now either you're just shy or, well, that's good, but I'm going to hold you to it. So if you have the elastic potential energy, or, well, for that matter, the work I did got converted into potential energy, which is going to get converted to kinetic energy, and energy is conserved. So force times distance, I didn't give you this one for elastic potential, and this one. So if you set them equal, and you knew this one, you knew the mass of the ball, you could figure out how fast it was going. And if you know how fast it's going, you know how far it's going to go. Which we're going to get to more. So let's shoot it, see where it lands. Help me spot it, because we'll just have to guess at this point. What do you think? There-ish? Middle of that? Thank you. Oh, way over here. I should have just stayed there. All right, that's 60. That was like the components. So it had a velocity like this. And if we take the components of that, you drop it perpendicular to this axis, and you get the length of the vertical. Right? Let's just say it's this. And then it had a certain horizontal. But it had more vertical velocity than it had horizontal. So it went up more than over. Right? Let's switch it and do 30 degrees. Where do you think it'll land? Close enough. All right, we'll put the same amount of energy in. 1, 2. All right, you ready? It still lands in it. Observations, though.
It hit the wall of the...
Yeah, that one hit more over here, didn't it? The 30 degrees went a little further. Maybe it was a fluke. Let's do it again. I have a plumb bob here. It's like a string with a fishing weight, so it just hangs straight down. And there's a angle here that was calibrated, so this angle right here is 30 degrees. Convenient. So I can just tip it until it lines up with the angle. No, it still goes further. Why the difference? That's not a mistake. The 30 went a little further, slightly, than the 60. Why? Okay, it didn't go as high, but why does that mean it didn't go as far?
It hit the wall.
That's right, it hit the wall. What's that? The 30 has more horizontal velocity. 60 had more vertical. Any other thoughts? Not exactly. So a neat little trick is that ideally they should go exactly the same. So if you had 60 degrees versus 30 degrees, get that? They ideally should go exactly the same. And that works if the two add up to 90. So it also would work with 75 degrees and 15 degrees. Those should land at the same spot. But not the same spot as this one. But that always works this. So they might do this. 75 might be like that, and 15 would be like that. They'd both land here. So what's different, though, is in real life, this isn't ideal. And it's sufficient you can notice it. This one didn't go as far because something was retarding it. Something was pushing back on it so it couldn't go quite as far. What do you think that was? Very good. Air resistance. It's real. It's not big, as you can see, but it's there. It's not negligible in this case. Can't, or you guys wouldn't be sitting here watching me be croaked because you can't breathe. But why did it affect the 60-degree angle more than the 30-degree angle?
Longer time in air, so it's subject to the air resistance longer.
Excellent. That's exactly right. The 60-degree one is in the air longer. It's in the air for more time than the 30-degree one. Even though they go the same distance down range, the range is the same ideally. This one takes longer to get there because it spends more time in the air, more time for air resistance to slow it down a little. So the 60-degree one we saw didn't go quite as far as the 30-degree one. It'd be the same with 75 and 15. But there is that neat little trick that if they add up to 90, ideally they should land in the same spot. If you start and stop at the same height, what you probably already know, the ideal angle to go the furthest would be what? Yeah, 45 degrees. So, I don't know, there-ish. And it would go further, ideally, if they start and stop at the same height. Guess we could do that one, huh? Let's see if physics is true.
What happened if you put the box a little further? More to the other side.
If I did put what?
Move that box a little further.
Would that affect how far the ball flew?
I don't know, I'm curious.
What's making the ball given it its energy?
Yeah, the thing to me, the wall hits the wall.
Oh. You're saying the 30 could be landing over here. Yeah. That's true. That's true. Which means it's even a bigger difference. Proves my point even more. I'm going to leave it there for reference when I shoot the 45. Same amount of work put in, same amount of energy stored. Put it back to 45 because I bumped it. And in theory, this would go further. Now, at a 45-degree angle, how do the two components compare? They're equal. Right, because it's going exactly, splitting the difference. Yeah. Went further. So when you start and stop at the same level, and 45 is more effective at getting further. All right, another thing I'd like to emphasize. We talked about it with the monkey shoot. Well, I want to do it again. Let's say you're shooting out of a cannon here. Poof! And without gravity, it would have that trajectory, correct? Because inertia. If nothing acts on it, it would just keep going at a constant speed in a straight line unless or until a force acts on it. So let's say... But you guys, well, you know in reality which way it will go. It'll start heading up, but then it'll fall back down, right? Because gravity acts on it. It'll make a parabola. So let's say it takes a second to get, oh, I don't know, here. Okay, if it takes a second to get there, and we turn on gravity, how far will it get on the real path? Here? Here? Here. Will it go further? Yeah, it goes that far horizontally. Because the horizontal velocity doesn't change, right? Let's to emphasize that again. This starts out with some velocity in that direction. That's the y part component. That's the x part. It keeps that the whole trip. Because there's no force acting on it horizontally. If you minimize air resistance here. Vertically, you know what happens. That one slows down, comes to a stop, and then speeds back up. So what I'm getting at here is if it takes a second to get this way, straight, and you turn on gravity, another second it'll take to get there, it's as if it fell from that point for 1 second. This is 1 second. And do you remember how far something falls from rest at 1 second? For 1 second? 10 meters per second, because that's the acceleration. 10 meters per second, every second. That's the acceleration. So that gives you the change in velocity. Yeah, it would fall. I mean, it would be going 10 meters per second if it fell that far. Do you remember how to find how far it had fallen in 1 second? So you're right, we drop a ball and after 1 second, it's going 10 meters per second. But how far did it fall? There were two ways to look at this. Sorry, I was talking over you. Yeah, there's that equation that the distance is 1/2 acceleration times squared. We learned it was proportional to the time squared. This was my example of like my sister-in-law spitting off the San Francisco Golden Gate Bridge or dropping a rock in a well. And if you time how long it takes, you know gravity. You know how far vertically it fell. So we could do that. 1/2, 10 meters per second for 1 second. And what do you get? 5 meters. It would fall 5 meters. The other way to look at that is average velocity. Good review, right? If it started at 0 meters per second, that's the initial velocity, its final velocity after a second of falling is 10 meters per second, what would you say its average velocity is? 5. So it's as if it went that distance going 5 meters per second the whole time. Didn't change. That's what average velocity is. And if you go 5 meters per second, how far do you go in 1 second? 5 meters. So same answer. So there's 2 ways you can look at that. So that's how far it falls. It's as if you didn't have gravity. It would make it that far. But we turned gravity on. So it's as if it fell 5 meters in that same amount of time. And so it ends up there. If you went another second, you're over here somewhere, and it falls, if this were a 2, what would we get? 2 squared is 4. 4 times 10 is 40. Half of that is 20. So it would have fallen 20 meters. So again, without gravity, it would have just continued on for another second. But with gravity, it's as if it fell 20 meters. And so it ends up over there. Whoops. And so on. I just think that's neat. Another way of visualizing for some of you that two-dimensional motion is just 2 separate one-dimensional problems. You deal with the horizontal, you can deal with the vertical. They're independent of each other. All right, clickers. Let's test you on some of this. Check your understanding. Oh, right. Some of you still haven't contacted me. I'm not sure why. B84. D83. These are device ID numbers that are still unassigned. Thus, if this is yours, you're still not getting any credit. So please talk to me. 110. And some of you have still been here the last 3 lectures answering, but haven't told me anything. 635. Just come down and tell me or send me an email letting me know. B85. Most of you are good. These are the 3 that are still unassigned. All right, those 3. I'm connecting to ResponseWare. Get a session ID number. Got it up. Dim the lights. If what? What happens what? Okay. Anybody need more time to log in? Sure, that's why I asked. Actually, that stays up. I can go ahead and open this. Some people can start while you're still. So polling's open. You can begin answering if you're set up. Now, I won't lie, this isn't a simple question. You have to think of the 2 types of motion, horizontal and vertical, and put them together to get this answer. So that's a clue. So this thing leaves the cannonball horizontally at 10 meters per second. you know which way it's going to go. It's real path. It's not going to stay straight and horizontal, is it? It's going to start curving down to the ground. Make a parabola, or half of one. So I'll even give you its speed 1 second later is what it's asking. It's not asking for its components of its speed, horizontal and vertical. It wants to know combined speed. So this isn't just the horizontal. This isn't just the vertical. All right, looks like we got most people. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. All right, we got 10 or 20 are the big majority. Okay. Let's draw a picture. So it's like you shoot something out of here at 10 meters per second. So initially all of its speed is horizontal. Which way will it go? It'll drop down, right? 1 second later, it's like without gravity it might be here, and then it falls. So let's say 1 second later it's over here, ish. Now it's pointing this way, and its speed is this. That's what we're asking. It has, here, draw some x and y axes. It has a horizontal component, right? It's still moving horizontally, but it's now also falling, so it has a vertical. You got Vy, Vx. Velocity in the x direction, velocity in the y direction. It's asking what is its speed 1 second later, this thing. So help me out. What do you think its horizontal velocity is over here? 10. It shouldn't change because there's no force acting on it horizontally. So it's still 10. Or in real life, slightly less because of air resistance. It'll be 10 horizontally the whole time, right? What will its velocity be here 1 second later? Vertically. 10 meters per second. Remember we just did that. That's how far it falls in 1 second. What? It falls 5 meters and is picked up, changed its velocity by 10 meters per second. So it'll be going 10 down also. So I didn't draw this to scale. Let's redraw that. Let's take this spot right here and zoom in on it, right? It's like, so you got 10 this way, and you got 10 this way. Does that make sense? Why it's 10 both directions? So it's going to end up over here. And that's what I asked you. I actually would have accepted answer B or C. The correct answer is B, 14 meters per second. But 16 is close, and since we haven't done that type of math before. So obviously I needed to teach you better. Because the majority of you guys did A and B. So you can't just add these together and get 20. But you do have to consider both. So again, horizontally it doesn't change. It's still 10. But it's falling, and after a second it's now going 10 meters per second downward also. Thus the resultant combined velocity is represented by this length. Remember the length of vectors represents magnitude? You can see this is more than 10. So from this the answer can't be A. But it's not twice it either, so it shouldn't be D. It could be 14 or 16. That's why I was going to accept either. If you do Pythagorean theorem for right triangles, the square sides, 10 squared plus 10 squared equals the hypotenuse squared. If you solve that, you get this to be 14 meters per second squared. But eyeballing, by drawing a picture, it looks about 14-ish compared, if drawn to scale. Questions, concerns? You sure? Yeah. Okay, thank you for asking. How did I get 14? And we haven't done that before. Do you see that it's bigger than 10? Do you see that it's not quite 20? Then I'm happy. For a right triangle, let's focus in on this guy. Let's say. Here's the right triangle. A, B, and C. A squared plus B squared equals C squared for a right triangle. So this is 10, this is 10. So 10 squared is 100, 10 squared is 100, you get 200. The hypotenuse is 2 squared. The hypotenuse squared is 200. So you'd have to square root both sides. The square root of 200 is 14. I'm not asking you to do that. So drawing pictures helps me again. At least by drawing that I can see it's more than 10, it's less than 20. And drawing this too helps me realize, I got to deal with both things going on. Anybody else? Yes, Patricia? If the angles aren't 90, you have to use trigonometry, which I'm not asking you to do in this class, with sines and cosines and tangents. But you can still get a qualitative answer by drawing the triangles, because this still works. For example, let's say you had this and this. We talked about this earlier where it's the parallelogram rule. This just parallelogram happens to be a nice square. So you draw parallel lines and another parallel line. And you can see this parallelogram. It's going to end up going there. And so you can get a relative. It's a little longer than this one. It's a lot longer than that one. So if you knew these values, you could approximate it. And that's all I'll ask in this course. I don't intend to do that, though, with this. Good. Okay, let's ask another one. Number 6. All right. Go. Give you a chance to read it. For those of you that it doesn't make sense, you're flying in an airplane. If the wind blows from behind you, you go faster. If it blows in front of you, it slows you down. What if it's coming at a right angle to you? What if the wind's blowing at me from you while I'm moving this way, at a right angle? What will that do to my velocity? Draw a picture if it helps, because I'm going to. Got a plane with some velocity. If the wind's coming at it, it's like a force pushing it downward, sideways. What will that do to its speed? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And okay, you guys are split. Well, good. I'm glad I chose these questions. The answer to this one is increases. Let's look at that. Okay. So we got a velocity this way. Is the wind going to affect the engine? Is the engine going to still put out the same amount of energy and force it's been doing, or does the wind affect that? No effect. It's still trying to do the same thing. So it's going to maintain this this velocity horizontally, straight ahead. But we have an additional force. The wind's now blowing sideways. So it's going to cause it to go down or sideways a little bit also. Does that make sense? And can you see where the resultant will end up? It's going to start blowing. So instead of my example, the wind's coming at me from you, plane's moving this way, I'm happy, and now there's a side wind. I'm going to start going this way, aren't I? So I have that forward velocity component and a sideways velocity component. Forward and sideways. It's going to result that I go diagonally, catty corner. And can you see, this is longer than that. It's increased my speed. It's as if the engine is helping it go forward and the wind's helping it go sideways. So relative to the ground, it's now moving faster. It still has the same speed horizontally. It won't get there any faster, if it's going straight. But it is moving faster relative to the ground because it has a forward motion and a sideways motion. So it's going diagonally. Does that help? Questions? So the idea here again is everything you've learned, it still works. It's not any harder. You just kind of have to do two of them. You have to, if something's going in a two-dimensional direction, you can't just deal with one. You have to deal with the other also. Okay? I got another one. Check your understanding. Not that one. I want number 14. All right. When no air resistance acts on a projectile, so it's ideal, its horizontal acceleration is so we're just asking about the horizontal acceleration this time, not the vertical. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. A lot of you haven't voted. Get them in. 3, 2, 1. Okie doke. All right. Most of you say 0. Very good. The velocity doesn't change horizontally. There's no force acting on it horizontally, especially in this case because there's no air resistance. So there's no force acting on it. Force causes things to accelerate. If there's no force, no net force, there's no net acceleration. If there's no net acceleration, it doesn't change its velocity. It just keeps going at that speed. So the horizontal acceleration is 0. What is it vertically? G, it's gravity. If it vertical acceleration would be 10 meters per second, G. One more. Nope, I lied. That was all I wanted. Okay. I want to show you a little video as an intro for relativity. There it is. No more questions today. You can put your clickers away. This little video was made in 1960, but it's still very effective. It's about 8 minutes long, and it's a great introduction and transition from what we just discussed to relativity. And then we will obviously get into it more.
Seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You... No. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands. That's a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. This is that all motion is relative to the wall, and the wall was moving relative to me. All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things. This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object, such as this ball, can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines, which we call horizontal or level. In this film, we're going to look at the motion of objects in this earth frame of reference and in other frames of reference moving in different ways relative to the earth frame. Well, let's look at a motion. This steel ball can be held up by the electromagnet. Now I'm going to open the switch and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line. As you can see, the electromagnet is mounted on a cart that can move. And I'm going to do exactly the same experiment that Dr. Hume did, but this time while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity. When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. Now, I want you to watch right here so that you will see the ball falling.
In line with the post? Won't be behind the post?
I think you can see that the ball landed in exactly the same position that it with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. ball was released at that point, straight down. Because the cart moves on in the time that it takes to fall, it would have landed back here somewhere, but it didn't. Now I'm going to do the experiment again. This time, through a slow motion camera, which is fixed here, moves by, the ball will fall, and you can watch in the slow motion camera. I'll show you this again. This time there'll be a line on the film so that you can see the path.
Oh, it's dark. I meant a little further back.
There'll be a line on the film so that you can see the path.
So, good for you. The ball still has horizontal velocity, but then it gains vertical velocity as it falls. And so, yeah, it forms that parabola. It's not dropping straight vertically because it still has inertia horizontally. And you can see it here from a different frame of reference.
I think that you can see that the path of the ball is a parabola. But all of this has been in a frame of reference fixed to the Earth. How would this motion look in a frame of reference which was moving along with the cart? Frame of reference. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. Like this. I'm going to do the experiment again. And incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point. In the moving frame of reference, I think you could see that the path of the ball is a vertical straight line. It looks exactly the same as it did before when Dr. Hume did the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a... I'm going to do the experiment once more, and this time I'm not going to stand here behind the ball as it falls so that you won't have any fixed reference frame. As far as you're concerned, that time, the cart wasn't necessarily moving at all. That time, when you couldn't see the background, it was harder for you to realize that you were in a moving frame of reference. The important thing to realize here is that all frames of reference, moving with respect to one another, are equivalent. Dr. Ivy showed you...
All right. That little 8-minute segment was very pertinent. So dropping the ball was almost exactly the type of experiment that when we did the cart that shot the ball up, and since it had horizontal velocity initially, it went still going horizontal and up at the same time. And so it stayed with the cart. But his idea, if we could strap a camera and ride along with the cart and be in a different frame of reference, moving with the cart, what would we see? Yeah, we would just see the ball go straight up and straight down because we're moving with it. And like at the end there, if you had no reference that was fixed, if you guys all disappeared and we couldn't see anything but the ball go up and down, we could not distinguish whether we were moving or not. Because we would see the exact same thing if we weren't moving, right? It would go up and down. And if we move, it goes up, it goes down. If we don't have something to compare to, it doesn't matter. So all motion is relative. And any reference frame moving with a uniform speed, constant velocity, in other words, not accelerating, no one is special over the other. There is no absolute fixed reference frame. Like they said, we like to use the Earth because that's where we live. But even the Earth is moving. It's rotating. It's revolving. The solar system's going around the center of the galaxy. Our galaxy is moving. There is no absolute reference frame that we can compare to. So all motion is relative to some other reference frame. And no reference frame is the main special one. This is how Einstein started coming up with a special theory of relativity. And that's one of his postulates. It's based on two main postulates. The first one, a postulate is an assumption, given this, and then a second one, all this other things must happen. He used logic. And the first one is that. No reference frame is special. All motion is relative. No one reference frame is preferred. And since all the laws of physics work if we're not moving, they all seem the same if we're moving at a uniform speed. The laws of physics are the same. That was helpful because you don't have to relearn something if you hop on a plane. You don't have to adjust how you're throwing things because you're now moving. You can toss a ball up and down on a train or an airplane, right? It comes right back down to you. It looks like it goes straight up and straight down. Relative to the Earth, it's doing this, right? Because the plane's moving, but you're moving with it. So all motion's relative. You can't tell these things. That's his first main postulate. They did an experiment, Michelson and Morley, and if you have not been following along in your book up till this point, I strongly encourage you to read chapter 35. It's excellent, because people don't get this as quick. But they did an experiment to test this. The Earth is moving fast. It rotates. One side's going faster than the other relative to space. Or if it's in its revolution, its orbit. You know, if space is here, maybe it's going faster this way than this way. Let's say the space is moving that way. It's like a plane traveling in the wind. Well, if you're going perpendicular to it, you might get this velocity. But if you're going with it, you'll be going faster. If you're going against it, you'll be going slower. So they devised an experiment, explained in more detail in your chapter, with light. They wanted to measure the speed of light, and they expected to get a difference. This was one of the biggest failures of an experiment in science. They got the speed of light to be the same in all directions. It didn't seem to matter whether the speed of the Earth added to it, or went against it, or sideways. They always got the same value. They checked their numbers. Other people have since repeated this. They didn't mess up. It was a failure. But from that failure, we have learned more. It's been one of the pivotal experiments, and that's what led to Einstein thinking that no reference frame is special. All the laws of physics hold in every uniform moving reference frame. And the second postulate, the speed of light is the same for everybody. If I turn on a flashlight, there goes the light, and I measure it, I get the speed of light. If I'm cruising around on a spaceship and I turn on a flashlight and measure the speed of light, I get the speed of light. You know how when you're on a truck, I know we're ending, and you're going 50 miles an hour this way? If I throw a baseball at 100 miles an hour, relative to you, how fast is the ball going? Truck 50, ball 100. Truck 50, I throw it that way at 100. Relative to you, it's going 150. Because the truck's moving, and with light, that would not be true. If I turned on a flashlight going on a rocket ship going 100 miles an hour, and I turn on this light, you don't add them. The speed of light is constant in every reference frame. Everybody would measure the same thing. That was weird. But this experiment kind of proved it. And those two postulates lead to the whole special theory of relativity, which we get to get into now. What does it mean? What will that imply? We'll do that next time.